Right now begins the podcast on projectile motion. And what is projectile motion? Hey, Mr. G, that's a good question, the funny little mouse says. So after watching this, you should be able to recognize examples of projectile motion, describe the path of projectile motion as a parabola, resolve vectors into their components and apply them to problems involving projectile motion, and apply the kinematic equations to problems involving projectile motion. Now, projectile motion is a combination of your x direction stuff and your y direction stuff. And that's probably the most confusing thing about it, just recognizing that and breaking it down to seeing that only x stuff happens in the x direction and different stuff happens in the y direction. So projectile motion is two-dimensional motion. So the vertical, all your y component stuff, so y stuff. And your horizontal, all x stuff. Now we're using the same free fall equations for the vertical stuff and the same kinematics equations for the x direction. The only thing they share in common is time. So time is common in both directions. So when we're finding the time, usually in seconds, it is broken up into x direction stuff and y direction stuff. The time is what they both share. Now, they're each going to have their own velocity. You're going to see like initial velocity in the x, initial velocity in the y. Like that's why all these little subscripts are on your equations. X, y. So types of projectile motion: horizontal, it's motion of a ball rolling freely along a level surface. And your horizontal velocity is always constant. So what that means is your v initial in the x always equals your v final in the x, because there's no acceleration, because a equals 0. Now vertical, we're treating it just as a free fall problem. So you can see this, the blue ball is the actual ball. And we can see it falling. And we can represent its vertical motion just with this red ball, how it gets faster as it goes down because gravity is pulling it down, so it's accelerating. Now the vertical motion, the horizontal, it's a constant rate. The same distance is covered in each one of these little time segments, because its final velocity and initial velocity are the same because there's no acceleration. But as it's falling, the distance in here increases between each successive second. So just like with free fall motion, all your y stuff, and just like with kinematics, all your x stuff. And it makes a nice parabolic path. And if you remember from math class, parabola are like those nice curved lines. So when we combine the horizontal with the vertical, you get a parabola. So a couple examples of projectile motion. We're launching a cannonball, and we're shooting it horizontally, so launched horizontally. You're going to see this word a lot, or these combination words a lot, launched horizontally. When something is launched horizontally, that means it's the angle it makes with the x-axis when it's being shot is 0. Because it's launched perfectly horizontally. So when we're doing these problems, notice how the velocity in the x direction is 20 meters per second the entire time. But the velocity in the y direction increases by 10 meters per second after every second because gravity is pulling it down at roughly 10. So if something is launched horizontally, you're going to want to find all the x stuff and y stuff independent of each other. So just how we did inventories for free fall and for kinematics problems, now we have to do inventories for both stuff. So my x, so my initial position in this problem in the x, we don't know how far it goes, so that would be a question mark. But its initial velocity is going to be 20 meters per second in this case. Final velocity is going to be 20 meters per second because acceleration equals 0, and you're going to have time. So really the only things you ever have to write down in the x direction, you're going to try to figure that out. Sometimes they'll give you this, sometimes you got to figure that out, in time. So you don't have to write down acceleration because we're always going to have the same acceleration of 0. Now when you're doing your y stuff, you're going to have to write down everything. Your delta y, your initial y, and if something's launched horizontally, your initial y is 0. Because just like we're holding a ball in the air and we drop it, if we're launching it horizontally, it means all of its velocity to start is in the x direction. That means its initial velocity in the y is 0. Final velocity, the y, you're going to have to find. If something's just in the air, gravity is still 9.8. Might throw a problem in there where it's something on the moon, and gravity will be different in time. Now remember, this time and this time are the same time. It's the only thing these guys share in common. You can also have a projectile that is launched at an angle. See, this guy is initially launched with a velocity in this direction. What do we do with things at angles? We break them into their components. So this guy, there'd be an angle in here. It's going to have an x component of velocity and a y component of velocity. Now these components are going to be the initial components. So we just use our trig stuff. Vx is going to be equal to whatever our velocity is times the cosine of the angle. And VIY is going to be whatever the velocity is times the sine of the angle. So something launched at an angle is going to have both initial velocity in the y and initial velocity in the x. And we can see, we draw a little coordinate axis in here. This is plus x, plus y. So our initial velocity in the y is going to be positive if we launch up at an angle. Something else you also want to notice. Pay attention to the horizontal arrow as it's going up. The horizontal arrow does not change length. It stays the same thing the whole time. That's why it has right here, v in the x direction is 60 meters per second. Because it stays the same speed the entire time in the x direction. However, notice its y velocity. It starts to go down. It decreases, 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 decreases until it reaches its highest point, which is right here, and its velocity is 0. So at its highest point, velocity is 0. Velocity, y direction equals 0 at highest point. Doing lots of problems like, I might say, how long does it take to reach its highest point, or how far is it above the ground at its highest point? And you're going to know that its velocity at its highest point is 0. So you watch the arrow. This is also important. Notice how the arrow in the y direction starts upwards. Let me clear this. And then it ends up going downwards. One more time. You see it's big, it gets smaller, 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 0, then it starts pointing down. That indicates the direction of its velocity. So as it's going up, its velocity is positive. As it's going down, its velocity is negative. Also important to know. Watch those negative signs. Equations. X component stuff. This is the only equation you're ever going to have to use in the x direction. That guy. Equation number 1. This is also written as just this, because delta x equals x final minus x initial. This is the only equation you're ever going to have to use in the x direction. That means most of your work is going to be done in the y direction. And those are just the same equations from your free fall. So remember, y final minus y initial is your delta y. So it's just the same free fall equations. Now, the common thing I said was time. So generally, in most of your problems, you're going to have to find time using one of or a combination of these equations. And usually I have to plug it back into something up here. Sometimes I make it easy and I give you this guy and this guy, find time, and then I have to find something else down here. But usually you have to find time using one of these two equations or a combination of two or more of the equations, and then set it back up in this x component stuff. So note your gravity 9.8 meters per second squared because it's, gravity on Earth. I'm the only one allowed to use 10. Do not use 10 on your problems. And if something's launched at an angle, you can find your initial velocity in the x direction, vi cosine theta, your initial velocity in the y direction as vi sine theta. So that just means here's your v initial at an angle. Remember, anything at an angle, as soon as you see an angle, break it down into its x and its y components. So vi cosine theta and vi sine theta. So there are several things that affect projectile motion, actually only two. So the angle at which something is launched. So this guy in here, this little angle, you change that angle, you change how high it goes, you change how far it goes, you change how long it's in the air, you change everything. And also the initial velocity, which is also going to change how far it goes, how high it goes, and how long it's in the air. So we're going to do a quick example. An object is fired from the ground at 100 meters per second at an angle of 30 degrees with the horizontal. So calculate the horizontal and vertical components of the initial velocity. It's one thing we're going to do. You always want to draw this stuff out. Even if you can picture it in your head, it's best to draw it. So we're launching it at 100 meters per second, and it makes an angle of 30 degrees with the horizontal. After we do that, we're going to find out how far the object has traveled in the horizontal, the x direction, after 2 seconds. And we're also going to find out how high the object is at this point. So, part A was find the components. So we draw our vector. Since it's at an angle, it has an x component and a y component. And it was 100 meters per second. So VIY equals VI sine theta, VI x equals VI cosine theta. So we plug in our numbers, 100 meters per second times the sine, 30 degrees, and 100 meters per second times the cosine, 30 degrees. Pull out your calculator. I want my calculator to come up here. Calculator doesn't like me today, so I have to use a regular one. Alright, so plugging these in our calculators, make sure you are in degrees because we're not working with radians. I don't like radians. Science doesn't use radians. I don't know why they teach you radians in math class. So make sure your calculator's in degrees, which mine is not for some reason, which is really strange. Alright, so 100 times the sine of 30 and 100 times the cosine of 30. I knew these, I don't need to put these in the calculator. So 50 meters per second and 86.6 meters per second. So part B is how far did it travel in the x direction after 2 seconds. So we take our inventory. Delta x is what we're looking for. Our initial velocity in the x is 86.6 meters per second. Our time, 2.0 seconds. So we use the equation delta x equals VIX t. Plug in our numbers, 86.6 meters per second times 2 seconds, and you get 173.2 meters. We'll double check that. Yeah, 173.2 meters. So that's how far it traveled after 2 seconds. Part C is how high is it after 2 seconds, and that means delta y stuff. So we're looking for delta y. Our VIY equals 50 meters per second. Our gravity equals 9.8 meters per second squared. Our VF we don't know, and our time we do know. 2 seconds. So what equation are we going to use for this guy? Well, might as well just use this guy, delta y, since we don't know what the final is. Final velocity, VIYT plus 1/2 AT squared. So delta y, plug in your numbers. 50 meters per second times 2 seconds. Sorry, it should be minus g. So minus g instead of that guy. So minus 1/2 times 9.8 meters per second squared times your time squared, 0.0 seconds squared. Plug it in your calculator. Delta y is 100 meters minus 4.9 times 4. 4.9 times 4 minus 19.6 meters. So minus 20 is 80 minus. I'm just doing my calculators. I'm slow today. 80.4 equals 80.4 meters. So it traveled 173.2 meters in the x direction, and it reached a height of 80.4 meters. Now there's several other things I can ask you about this problem. I could ask you like how long it takes to reach its maximum height. Let's do that real quick. So VIY was 50 meters per second. So how long to max height? Can't spell today either. So we take our inventory, delta y we don't know because we don't know what our max height is. Our initial velocity in the y is going to equal 50 meters per second. Our final velocity in the y, what is the final velocity in the y at its maximum height? It is 0. Gravity, 9.8 meters per second squared. Long. And our time, we don't know. That's what we're trying to find. So what equation are we going to use for this guy? We can use this equation. VFY equals VIY minus GT. So our final velocity in the y is 0. Initial is 50 minus 9.8 t. We solve this guy for t. You get t equals negative 50 divided by negative 9.8, which is roughly 5 seconds. Now I could ask you how high it goes. So now that we know that, you can find the height in 2 different ways. You can either use this equation, or the other equation. We're going to do it both ways real quick, show you get the same thing. So using this equation, you plug everything in. 50 times 5 minus 4.9, which is 1/2 times 9.8, times 25. So 250 minus 4.9 times 25 Whoa. Yeah. Multiplied when I should have divided. 127.5 meters. Now if we do it this way, solve this guy for delta y. Hopefully getting better at your algebra skills. Over negative 2g. That's 0 minus 50 squared over negative 19.6. So negative 250 divided by negative 19.6. Why am I getting different answers? Oh, 2,500. Duh. 50 squared is not 250. All right. You get the same answer. So you can do it either way once you find the time. Or if I didn't ask you for the time and just asked you for the maximum height, you could use this equation. So you can find all this stuff out pretty easily if you know how to use your equations. All right, so solving problems. Here's just a quick little guide. Read the problem carefully and choose the objects you're going to analyze. So, whatever's being launched is what we're going to analyze. Draw a picture. Draw pictures. Pictures are good. They help to clarify stuff. I want to see pictures every time you do a problem. Choose an origin and a coordinate system. Because of the equations we're going to use, we're going to always choose the same coordinate system. Plus y up, plus x down. You can choose other ones, but I'm going to keep it simple. We're only going to use this one. Decide on the time interval. This is the same in both directions. Same in both directions. The same t for the x as the y. And break it up into x stuff and y stuff. So two different inventory lists. Your x stuff and your y stuff. All right, and when you're reading the problem, you want to look for key things like launched horizontally. What does that mean? That means its initial y velocity is 0, launched horizontally. Max height. We're going to know the final velocity. The velocity in the y direction at its max height is going to be 0. So those are probably the two most important things to look out for. Launched horizontally and maximum height. Because it might not always tell you when the velocity is 0 and stuff. So you have to infer that. Another step, list known and your unknown quantities. That's your inventorying. So remember, the velocity in x directions never changes. And velocity final, should be an F in here, equals 0 at its highest point, which I just said, at its max height. Plan how you proceed, look at your equations. You might have to use more than one equation, and usually you're going to be working with the y stuff to find time, and then plug it into the x stuff. All right, here's just a little conceptual kind of thing. So a child sits upright in a wagon, which is moving to the left. Sorry, moving to the right. The wagon's going this way at a constant speed. So constant speed, next direction. So constant speed going this way. The child extends her hand and throws an apple straight upwards. So throws an apple straight up. So while the wagon continues to travel forward at a constant speed, if air resistance is neglected, which it always is in our problems, will the apple land A, behind the wagon, B, in the wagon, or C, in front of the wagon? So she's going to be traveling in this little wagon. She's going to throw this apple straight in the air. Where's it going to land? Is she going to continue to go forward and the apple's going to land behind her? Is she going to continue to go forward and the apple's going to land right on top of her? Or is she going to continue forward and the apple's going to land in front of her? So what do you think? Think about it for a second. Imagine yourself driving in your own car and you're sitting in your car and you throw a ball up. How does that ball react? So the answer is it's going to land directly in the wagon with her. So when you throw this apple in the air, it's actually going to have an initial velocity at an angle, even though in her reference frame it looks like it's straight up. And since the x velocity never changes, and it's the same velocity as the wagon's x velocity, it's going to cover the same amount of distance in the same amount of time. So apple and wagon cover same delta x in same time, because they have the same x velocity to start with, and that velocity never changes because the acceleration is 0 in the x direction. That is all.